What's up, guys? Last video we talked about a couple functions that are recursive, or that could be recursive if you want to write them that way. The first was the Fibonacci sequence, 0, 1, 1, 2, 3, 5, 8, 13, 21, etc. And the way to make that is your next number is going to be the previous two added up. So like 34 is 21 plus 13, and then 50 whatever is 34 plus 21. That gets bigger quickly, but it should be fine. Computers can do addition, no problem. And when you write it like this, it appears the way that we think of it. In our minds, if we're looking at a list of numbers, we go, oh, you just look at the last one and the one before the last one and add them up. But when a computer sees this recursively, it's saying, oh, I want to find the 30th. Well, I have to find the 29th. Which means I have to find the 28 and 27, which for that means I have to find the 26 and blah, 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 all the way down the branches to the beginning, then doing that again. So it makes it super, super inefficient doing the same work many, many times instead of what we find here. I showed that you can make a cache and say, hey, Fibonacci of 29 is whatever, and when we have to reuse that in the next few, you can look it up in the cache instead of calculating it again. But I didn't quantify it. I just showed that this version runs out of steam at around 30 something, and this version can go forever, no problem. Let's do a timed trial. I imported a module called TimeIt, which I've shown a few times in here. And you just give it a function and how many times, which right now is just going to be 1, because this one's going to barely make it through 36. And as you'll see, it doesn't show up right away, because what it's doing is finding 1, 2, and then to find 3, it has to find 2 and 1 again. And to find 2, it has to find 1 and 0 again. And as it goes, it branches forever. So uncached, it took 13 seconds to find 36 numbers. And cached, it took, you might at first glance say 3. Oh, okay, it's like a quarter of the time. No, it's way better than that, because it's scientific notation. It's 3 times 10 to the negative 5th, so it's 0.00003, which is much, 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 much faster and better. So if we had to do anything with Fibonacci numbers, we definitely want to use this method to give our computer a lot less work for the same result. Or if we were going to go to bigger Fibonacci numbers, this one wouldn't even happen. It would just completely stall out, whereas this one would zoom by, no problem. Now, I also talked about factorials. I assigned that as like, okay, you practice this one, so let's show how that might go. I made a recursive factorial, which is not the only way to do it. Of course, you can make factorials with a for loop, and that might be just fine. But they do make sense to write recursively because it's always just n times the previous version. For a quick recap on what factorials are, you take a number times one integer down times one integer down all the way to 1. 8 factorial, for example, is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And these are used a lot in probability and permutations whenever you're finding how many ways a thing can be arranged. Like if you're peeling cards off a deck, well, the first one has 52 possibilities, but then once that's gone, the next one has 51, and then the next one has 50, all the way down the line. So you can say 8 factorial is just 8 times 7 factorial, which is just 7 times 6 factorial, etc. And if you want to run that, it can do it. It doesn't completely fall apart the way the Fibonacci ones do. We can go up to 200, for example, but it's not super fast. And if you cache them, well, it's much better. And this one, by the way, I'm running it a lot of times. I'm running it 1,000 times because it doesn't branch off the way the Fibonacci's do and become insanely complicated. So we can give it a few seconds and see how long it takes to do this 1,000 times. So it took 9 seconds for the uncached, which is terrible, right? If something takes 9 seconds on a computer, it better be showing me 4K graphics. The cached, not even half a second, no problem. And that's to do it 1,000 times. So when we're doing stuff like this, I know this specific example might be done with a for loop or something, but the idea is you can take the work you've done and save it so that you don't have to do it next time. If I go to google.com, then my computer isn't really downloading this image, or this one for the microphone, or this one for the profile picture, because they're cached, they're saved wherever the browser puts that stuff, and it doesn't have to do the work. If I cleared the cache, then it would take a lot longer the next time I go to google.com to download those. Now, it's still pretty fast. It might be 100 times as long, and it's still half a second versus, a tiny fraction of a second. But that matters. So caching is not just for math. It's not just for recursive functions. But it's for any time a computer does something that takes resources like time or processing power or just electrical power. And if you think you're going to do it again sometime soon, you might as well hang on to that for a minute. We could encounter situations where the cache gets too big and we run out of memory. So there are ways around that by, deleting ones that are old or deleting ones that are least likely to be used, etc. I was going to show there is a built-in cache in your Factorials. And then you can add this to your functions and it'll do it on its own. However, there are two problems. One is that it just does it by making a dictionary. So it's not anything fancier than what we've done. It's the same thing. Also, CodeHS doesn't have that. I believe it was added in version 3.9, and this is running 3.8, so I can't show you on the CodeHS. But anyway, if you do use that in some other version, then it'll just be making a dictionary anyway. It's not anything fancier than what we've done. Think about that, and we'll use it in our next project.